This video briefly covers how to calculate an orbiting object's period. This is also known as Kepler's third law. It is also important for us to define what an orbiting object's period even is, and it is the time that it takes for an orbiting object to complete one full rotation. So for example, the period of the Earth around the Sun is commonly known as a year. So let's now derive an equation to more accurately describe this orbital time. We know that our velocity equation is equal to a particular distance divided by time. We can then multiply, and the particular time that we are looking for is the period, which is represented by a capital T here. And the distance that we are looking at here is one full rotation, which is also known as the circumference, or 2 pi r. So we can expand this equation even a little bit more, since we know that the orbital velocity is equal to the square root of the gravitational constant times the mass of the central object divided by the distance between the two objects. And we can simplify and solve for the period, which is equal to 4 pi squared over the gravitational constant times the mass of the central object multiplied by the distance squared, or cubed, sorry. So let's do an example with this new problem. We want to calculate the length of a year, or one rotation on Mercury, with an orbital radius of 5.79 times 10 to the 10 meters. So we have our equation, and we can fill in our known variables. Take note that 5.79 times 10 to the 10th is the distance between Mercury and the Sun, because Mercury orbits around the Sun. And 2 times 10 to the 30th is the mass of the Sun. And whenever we have a big M, we always put the bigger mass, or the central object's mass. All right, and when we solve, we see that this time or period is equal to 7.58 times 10 to the 6 seconds. And just for comparison, the period for Earth is 3.15 times 10 to the 7th seconds. So the period on, or the year on Mercury is shorter than the period or year on Earth.